All right. So under the pages on the website, under class materials, we have, I think, links to previous year's Chem 203 exams. And so a very typical midterm might consist of an IR problem, a mass spec problem, and maybe in this case, it's going to probably be 2 NMR spectroscopy problems, and that's the closed book part of the exam. So that's, nominally about an hour, although I'm going to be very, very loose with the time on those. Many of the problems we've already seen. Oops, oh, you're not, okay, you're not seeing that page. So let me share that page. So that page, I guess, popped up in a separate window. So anyway, you have IR problems, mass spec problems, NMR problems in the closed book, and you've seen many of these problems. You've seen the sort of matching the IR spectrum problem. You've seen this isotope pattern problem. The good ones get distilled into the homework. Let's see what else. What else is cool? No, you haven't seen this problem, but it's a good example of a characteristic problem involving recognizing some patterns in the NMR spectrum. And then there'll be some basic structure determination problems usually, and this part is open book, open note, but no use of the internet to look up formulas or the like, other than maybe the mass spec and calculator for high res mass spec. And so very typical sort of structure determination problems with a template, some data, some NMR data, and we're only running up through 1D data, so typically proton NMR and depth. So all of these problems are here linked to the website, and you're welcome to have a look at them. Heck, you're welcome to work them all.
If only, yeah. Thank you. That's an amazing resource. Awesome. And then just to clarify for the closed book, or for the open book, open note, open-ended, by the mass spec calculator, you meant what's it called, ChemCalc and the molecular formula finder?
Yeah, and you're welcome. And you're welcome to use your books. You're welcome to use your notes. You're welcome to use the lecture videos. You're welcome to use ChemDraw to check.
And then presumably then we can use our my favorite friend and tool, the spreadsheet you developed.
Absolutely, not for the first part.
Yeah.
But for the second part.
Totally understood. Thank you.
And my plan on this is, so this will be this weekend. And my plan on this is basically on Saturday morning at about 9 o'clock or at 9 o'clock, send out part 1. So basically send out part 1 and let people work on that on your own. And honestly, the timing is very loose. It should take about an hour, but nobody's, you may need some extra time to print it, or it's just slower. I'm not holding a clock to that. And then once I get that email back from each person, I'll send them part 2. And then part 2, honestly, should be done on Saturday. I think I think that's pretty reasonable by the end of the day, although again, I'm not going to, you know, if for some reason more time is needed, I think that's fine, but hopefully by Saturday night I could have it. So on Sunday, I'd have a chance to go over them. And that's all going to be done by email rather than by the website. So it's basically email it and email it back. Does anybody here need need to drop off a paper copy? I know a few people have been doing that on the homework. Everyone's good with scanning or working them electronically? Well, I guess.
If I mention something?
What's that?
You mind if I mention something really quick?
Yeah.
So I got an email from a student earlier this week. They were just asking what information should they expect to have memorized for part one that they wouldn't have or be given a resource for. So I was thinking the alkene IR problem, we gave them the table because that problem was about using the table, but what information would need to be memorized? As far as formulas, I could only think of degrees of unsaturation, but for other information, diagnostic, IR shifts, MS isotope abundances, and NMR, sorry, I used the wrong word for IR, but NMR shifts and splitting patterns.
I would agree completely. So my philosophy on this is pretty much for highly specialized information, you can look it up, or if you're going to be working with a ring system, let's say you go into, you know, a group that's doing a lot of oxetane chemistry and like the van der Waal group, and, you know, maybe you have it in Silverstein and you don't use it every day, but if you're working with oxetanes, I'm sure eventually you're going to know cis and trans coupling constants and all the coupling constants on the ring system. But for this class, you probably can look it up. On the other hand, some very basic stuff like we've covered, you know, cis and trans alkene, axial equatorial coupling on a benzene ring, maybe a little bit of the coupling we encountered on pyridine rings. I think this is pretty handy to have a sort of knowledge of. You know, that acetyl pyridine problem was a great problem, for example, where you started to really read and look at coupling constants and chemical shifts and try to understand how things work together. The problem I just flashed up a moment ago on this aromatic coupling pattern was a great sort of example of a problem. And as James said, being able to work out a basic coupling pattern as we had done, you know, both on graph paper, you know, so we did this on graph paper in the multiplet guide and handout. And that's a very important skill too, to be able to understand basic coupling patterns or be able to recognize basic coupling patterns.
Yeah, I don't know about anyone else, but drawing those splitting trees is something that I struggle with. So I'll have to study and practice that using that multiplet guide. I think it's called the multiplet guide part that we had in the last or previous homework set.
Yeah, that's I think a very, very valuable one, you know, and working through that. And it starts, It starts pretty simple, and it also gives you examples where I've done this on the page. So I think that's a useful skill set. I think one of the things that, again, bouncing back to the website and to this page here. Let's see if I can pull this up. So, I've got a nice grid that I guess that opens in another window. That's fine. I will pop that open. One sec here. So yeah, that links. So you can go ahead and you can go ahead and write on this if you want. You can mark it up, and that's a good practice, I think. I guess I can't do it on my screen here. I could probably do it on my iPad, but that's a nice way to practice these types of coupling patterns. Yeah, I don't think I have the tools to do it on my screen. I need to do that on my iPad. Actually, give me a sec. I'll do that.
I have a quick question. So will we have homework due on the Monday after the exam?
James, how do we want to handle the homework deadline?
I think one thing we did in winter was we just extended it to be due on Wednesday.
That sounds like a very, very fair solution.
It's also definitely shorter than last week's. I intentionally front-loaded problem set 5 to have a bunch of stuff that would be helpful for the midterm, and then deloaded problem set 6 because I knew it would be coming right afterward.
Thank you.
Hold on one sec. Let's go through an example over here.
James, would it be all right if after this I sent an email to the whole class letting them know how to access the previous year exam problems?
Oh, would you please? That'll be absolutely fantastic.
Because we both forgot to mention it on syllabus day.
Yeah, I thought I had, but I guess I hadn't. Okay, so coming back to your comment, Chris, you can put me to work, although hopefully not being too cruel to me, and we can take a look at an example here. So what would...
All right, I happen to have the most recent homework set out. Give me a second to flip through and then find something reasonable. Give me a second. How about either glycerol or the 3-acetylpyridine. Is there anything in there that's reasonable?
I think so. So what would you like me to sketch out for you? Do you have a particular multiplet that might be good, like from the guide?
No, maybe part of it is also I don't even know the right questions to ask. I don't even know like where to begin.
Well, let's go ahead. I'll try like a DDD.
Okay.
Let's say 14, 10, 3 as an example. Would that be a
Sure.
good one? So if I'm doing one box per square, I might split for my 14 and make a splitting tree where I go over 7 and 7. So that's going to be 14.
Hey, James.
Yeah.
Nothing's changing on
Oh, interesting. Oh, how interesting. Let's try this again. Because it normal, oh, maybe I had the wrong, okay. That explains it. I was looking at a grid that was up there, but it was my previous projection. So I was saying, let's go ahead. I'll just start this over again. So I said, let's pick an example, and maybe we'll do a doublet of doublets with 14, 10, and 3 hertz. And so I might go over 7 and 7 to get my 14. And then I might split each of these out by 10. So I might go over 5 and 5. So that's my 10. And then 3, so I might go over 1.5 and 1.5. And then I might bring the whole thing home by going ahead and representing this thing automatically draws.
I saw what you were doing though. Yeah.
Draws straight lines, and it decided I was really trying to draw a straight line. Okay. So that would be my little sketch of a DDD 14, 10, 3. And of course, built into this is the fact that means the entire width of this would be 27. So if I was uncertain on myself, I could go ahead and say, okay, well, I've got 8, 16, 24, and then I've got another, 3 between the two, another 1.5 and 1.5. In other words, this total width is 27. If I were doing, say, a triplet, J equals 7 hertz, I would, of course, go out 7 on one side and 7 on the other, and I'd recognize the fact that we are 1 to 2 to 1, and if I wanted to check myself, then that whole width would be 2 times 7 is equal to 14, which is what I've drawn.
Yeah, that was also, you actually just touched on something that was confuzzling, which is how do we know if there's a peak in the middle? And I guess I'm starting to see, like, understanding the concept of a triplet and seeing what the splitting pattern is supposed to be. So I know roughly the pattern to be looking for, and I know the relative peak intensities. But translating that into what you've got here is something I'm still struggling with. And I guess I'm just venting and ranting, but I see this. This definitely is helping. Going back up to the previous one, the reason so another thing is like, okay, how do we predict what the relative peak intensities are going to be? And we're saying your point here is there are no coincident or overlapping peaks. Therefore, all of the peak heights will be the same. Is that correct?
That's exactly it. Now, in practice, these lines would have some width and they'd start to build up on each other. But in this particular example, had we been 10, 14, 10, 4, then we'd be in a different situation where you'd end up with two coincident lines, right?
Right.
So then we'd have a pattern that looked like this. Oops. Hopefully this thing won't try to help me out by fixing my lines, right? So here's our 14, here's our 10. And then in this particular example, these lines.
Right in the middle.
Would merge. And so if I were sketching this one out, I'd sketch it out. Now I'd go twice as high for that one. And so that would be a DDD 14, 10, 4.
Okay, getting better. Thank you. I'll definitely mull this over and dwell on it and practice this, but this is very helpful. And then in both in the two doublet cases in the real spectrum, we might also expect to see some sort of tenting.
You're saying if we've got, if they're close together in chemical shift, right? So we've talked about the AB pattern being the archetype. So, right. So if you had, let's say, a doublet, let's say you had a doublet at, let's say 5.5 ppm, J equals 18 hertz, and another doublet at, say, 5.3 ppm, J equals 18 hertz, and they were part of an AB pattern, then you might see, and I won't do a full 18 here because I think I'd run out of space, but I'll just sort of sketch it out. Oops. I'll sketch it out, not proportional, but you might see the inner lines bigger. So that would be one of our doublets where this distance was 18. I haven't drawn it as such.
Understood, though.
And then your other doublet, the inner line, also would be bigger. And I wouldn't expect you to be able to calculate the exact heights of the peaks, but knowing that you were seeing some sort of leaning in, and that this was at 5.3 and this was at 5.5. That would be very reasonable.
Cool. Thank you. Thank you. Thank you. Thank you.
So yeah, these are, and the reason, so let me stop sharing this piece of paper here. So the reason I'm doing this is because, you know, there's certain sort of conceptualization that you want to be able to have in your head, that if you don't have that conceptualization, if you don't have that sort of ability to read the spectra and the patterns are mysteries to you, where you can, you know, you can type numbers into my Excel spreadsheet, but you have no idea what's coming out or how those numbers are related, your ppability to read is compromised. It's one of the reasons why when I look at a spectrum and I look and maybe I see a triplet off at 1 ppm and my eye sort of fixes, okay, that's a 7 hertz coupling. Oh my goodness, we've got such a big coupling on this other doublet. What's making that big coupling? Or we've got such a teeny coupling on this other doublet. What's making that coupling? That's why I'm emphasizing this idea of conceptualizing and reading. You know, or being able to look and say, I'm seeing 12 lines in this multiplet, and some of them are bigger than others. You know, I think that could be a doublet of doublet of doublet of doublets. That proton must have 4 coupling partners. Ooh, how do we get 4 coupling partners? And starting to think in that way, or being able to look at it and another, you know, peak that's nearby and say, oh, these two are tenting into each other. Maybe they must be coupled, and maybe they're even geminal. Maybe there are 2 hydrogens attached to the same carbon that are diastereotopic. That type of recognition is very valuable as well. Now you can get tenting in from protons on adjacent carbons. They don't have to be geminal, but often the geminal diastereotopic protons are similar in chemical shift, and they often have a very big J value. So often it's pronounced for that. So these are the sort of subtle reading that I encourage.
James, can
Yeah.
you determine which proton corresponds to what shift if they're geminal and they're so close?
One can, but usually you need a number of other factors involved. So if you have J values and you have some information about the conformation, say maybe from the nuclear Overhauser effect, then you can start to sometimes figure that out, where sometimes you'll have, say, let's take a look here. Does everyone know Newman projection? So I'm Newman projecting for the amino acid phenylalanine. And so the compound that I've drawn, it was the same one that we've I think we used in one hypothetical example on spin spin systems. And so imagine that I saw the following. Imagine that I saw two resonances here, one for this hydrogen and one for this hydrogen. And these two resonances showed very different J values to this proton. One of them showed a J value of, let's say, 10 hertz. And one of them showed a J value of 3 hertz. So I could be pretty convinced that we were in a conformation where either the phenyl group was biased toward being here, or conversely, where the phenyl group was biased toward being here. So I might be able to get an idea. And then maybe through a nuclear Overhauser effect experiment, we could see proximity between the orthoprotons and the NH group over here. And at that point, I might be able to have enough information to say, oh, okay, this proton is the pro R or the pro S proton, and this one is the pro S or pro R proton. I might be able to get a good picture of which is which. So sometimes you can. And one of the things that we're not doing in this course, where most of our stereochemistry is being confined to cyclic systems, and I've specifically left out sort of acyclic systems. So the van der Waal group does a lot of interesting work, for example, with the synthesis of chlorosulfolipids, often compounds where you'll have, for example, a chlorine and maybe another stereocenter and maybe another stereocenter. And there becomes a whole problem of how do you determine the relative stereochemistry of these stereocenters. And at that point, this type of subtle use of a combination of coupling data and NOE data becomes critical, because you're having to assign each of these acyclic stereocenters. You may be having to assign your diastereotopic protons over here. So I specifically haven't been, and maybe one year I ought to include some simple stuff. So for example, in the Aldol, have you learned about you're not doing synthesis yet, but in the Aldol reaction, you can get two diastereomers. So if you imagine the, say, Aldol reaction of, let's just take tert-butyl propionate, imagine treated with LDA in THF, and then add benzaldehyde. Now you can get two diastereomers. You can get the syn and you can get the anti. And the question becomes, okay, which one did we get? Or let's say, as might commonly be the case, you might have a mixture that's, say, 4-to-1 in favor of one diastereomer. So you have both diastereomers. And then the question is, okay, is my major component the syn, or is my major component the anti? And so being able to do this type of analysis where you're analyzing the dihedral angle, trying to glean information about what the preferred conformation is and what the coupling constants are and what the NOEs are telling you, can become absolutely critical. Maybe one of these days we'll incorporate, essentially this exact example in the course, because it's a great example for a skill set that one ought to have.
Thank you, James. And I was just wondering, can we, for the dihedral angle, can we approximate that the J value would be similar to the axial and axial equatorial if it's
Absolutely, off of the Karplus curve. Now, if you remember back to your sophomore organic chemistry, so let's go ahead and imagine we're doing a energy potential diagram for butane. And we're looking at the relative energy as we rotate about this bond. In other words, we're going from 0 degrees to 60 degrees and rotating about. You've seen that, right, in sophomore organic chemistry? If not, have you done that in 201? No. Okay. So if this is your energy, or let's call it free energy, we'll call it 0. We'll call it G. And this is theta. And we go from 0, 60, 120, 180, 240, 300 to 360. And we start, I guess I had this in my handout on molecular modeling. And we start, I think we're at about 4.5 for eclipsed. I don't remember the exact number. About 4.5 for eclipsed butane, and we go down to about 0.7 kilocalories per mole. And then for this one, for this eclipse, we go maybe a little bit lower, and then we go to 0, and then the whole thing repeats symmetrically over here. So here's our curve. Okay, so the point is, as you get off, and I think this is about 4, I have this in my notes, but basically, as you start to get off of 60 degrees in this cosine wave, you've got a little wiggle room before your energy starts to really go up. But by the time you're off by maybe 20 degrees, so 80 degrees or 40 degrees, by the time you're off of that, it's going to go up a lot in energy. And remember, the magic number of 1.36 kilocalories per mole. 1.36 is a relatively big energy difference. It determines a 10-to-1 equilibrium. In other words, you've got a big fight against you to go up 1.6 kilocalories per mole. So other than as a transition state, you're never going to be here. And honestly, you're not going to be spending much time over here. Or to put it another way, you really have to distort that molecule. So most of your populations are going to be close to 60 degrees or close to 180 degrees, which means you can think of it sort of as a linear combination of 60 and 180 and 220 and 300 degrees. So when we see, let's say for that phenylalanine example, we see a coupling constant of 6 hertz or a coupling constant of 8 hertz. It's not that it's being held over here. It's that it's a linear combination of the phenyl group windshield wipering to one side or to another. So in that example where I said, imagine we have 10 hertz and 3 hertz, the reality is you're going to typically, most of the time, have a J more like, say, 6 hertz or 8 hertz, which means it's a linear combination of various dihedral angles, a linear combination of somewhere around here, somewhere around here, and somewhere around here. So most of the time you don't get something conformationally locked, which is why it's a subtler problem, as I said, for something like this, determining the stereochemistry, the relative stereochemistry of your Aldol outcome, because it's not going to be, oh, I just need to find which conformer it is. You know, the good news on the homework set, on the problems I erased, where we looked at, we looked at the cyclohexane diamine, where the 3 amino groups were either all on the same side of the ring, or where 2 were on one side and 1 was on the opposite side. You know, so it's the cis-cis or the cis-trans diastereomer. We could basically say, okay, we're going to envision the cis-cis triaminocyclohexane as a single conformer with all 3 amino groups equatorial. And we'll envision the cis-trans aminocyclohexane, triaminocyclohexane, as a single conformer in which 2 of the amino groups are equatorial and 1 is axial. And so that makes it a lot simpler when you sort of know what your conformer is, but that's not always the case, particularly in the case of acyclic stereochemistry.
Makes a lot of sense. Thank you. Thank you, James.
You're welcome.
So kind of just, piggybacking off of this problem, the glycerol question, we could technically say, those methylene proton, which one is which, based on its coupling constant to the methine proton?
You could, yeah. I wouldn't expect it of you. It's a challenge in its own right. But yeah, you could figure it out for the glycerol.
And that's what I was wondering, because if one of them has a larger constant, I was kind of assuming they must have that larger the anti, they must be closer to anti, as protons.
That would be correct. Or to put it another way, the greater population would be anti. And I sort of hinted at how you would do a linear combination when we talked about the Michael addition, the conjugate addition of aniline to nitrocyclohexene. And at the very end of class, I said, now let's imagine we had a situation where we had, a mixture of the 2 conformers. What would we expect for our J values? So that was an example of that.
I have a totally side, unrelated, but fun diversionary question. I feel bad maybe putting James on the spot, but other James Griffin, how at all do you use any of this stuff? What research do you do, and how does this stuff come into play for you?
So recently I've been TAing the graduate course Organic Spectroscopy, and so I've been I've been taking your midterm exam problems this week. That's where most of it's been coming into play. I haven't recently, but a long time ago when I made my first analog of the peptide antimicrobial tixobactin, I took very, very comprehensive 2D spectra. And so once we get into Toxy, which is a 2-dimensional technique that allows you to identify spin systems, will show you how you can identify individual amino acid spin systems within a peptide in order to determine, this is crazy, you can determine intermolecular interactions between assembled peptides using the combination of toxi and nosy, which they sound like silly names. They absolutely are. But once you understand what the acronyms mean, they'll make more sense.
That's super cool. So if you can do that like in their native conformations, you can get insight into the quaternary structure of these things, right? Is that what you're getting at?
Exactly. And we
Super
actually,
cool.
we had our group meeting last night, and the first of every month we have current awareness where people are assigned different journals and we present papers that were relevant to the group.
Yeah.
And someone who has previously taught this course as a TA presented a paper about in beta hairpin peptide structures, if you have residues that are adjacent to aromatic residues, specifically tryptophan, the pi environment of the tryptophan can sometimes really, like I was surprised, James, that it was up to 1 ppm for the, was it valine or leucine that was affected? Do you remember?
Yeah, it was leucine in that one. And that is one of the giveaways with some of our peptides, that we're having some really interesting folding where you're having effects of an aromatic ring. You know, thinking about Zing's turn unit, of course, his is a problem in acyclic stereochemistry, if you think about it. He hypothesized that adding a methyl with a particular stereochemistry would enforce a conformation. He's able to see the diastereotopic delta protons. He's able to see unique, well, we have been able to see, and the degree of magnetic anisotropy of those goes up to 0.6 or 0.7 ppm. So we know that that's reflective of folding in that situation. And then honestly, from the J values or the J patterns, we're able to further deduce the conformation of the delta-linked ornithine, which is basically a cyclic stereochemical. We assign the diastereotopic protons there. So that's a perfect example, although, you know, more conformationally constrained than the Aldol one. So yeah, I guess James isn't using that right now in what he's currently doing, although, you know, one of the things we've never done in the SN2 displacement on the D-allothreonine mesylate to the azide, we've never sat down and really tried to prove those two stereocenters that way. And of course, Yang did it in a functional assay. You know, so we took on good faith that SN2 displacements work as textbook, but we could have sat down and done that, at least for the relative stereochemistry of those two stereocenters.
Very, very cool. But so it kind of seems like that there could be a second part to this class that goes into looking at just peptide structure individually or protein structure individually.
Very good point. You could indeed. And we're specifically doing 2 carve-outs in the class that we're not including, probably because we're on a quarter system rather than a semester system. Totally. So we're not doing proteomics by mass spec, which is something that probably we should think about adding, where you're basically dealing with using mass spectrometry to figure out the sequence of a protein. And we're not doing protein NMR spectroscopy, where we are trying to figure out the 3-dimensional structure of proteins. So you know, I call this organic spectroscopy because the primary focus is building the skills for people who are going to be working with small molecules, but those skills are also portable. But we certainly could be doing a biomolecular spectroscopy class. And if that were the case, I'd bring in other techniques like CD spectroscopy as well. And that could be very useful. And a lot of heteronuclear NMR, including N15 isotopic labeling and C13 isotopic labeling.
For the unfamiliar, CD spectroscopy stands for circular dichroism. And because amino acids are naturally chiral, if you have a peptide, the supramolecular structure of a peptide or a protein that's folded, you have beta sheet-like character, alpha helix-like character, and because they're chiral, they have characteristic absorbance of polarized light. That's what circular dichroism is used for.
Anyway, thank you both for humoring me on my little diversion.
You're very welcome. I think on this note, given that it's 9:53 and we are on Veterans Day, I think unless there are any final questions, I will be signing off.
Thank you for your help. See you Friday.
Thanks, James.
See you. Bye.
Thank you.
Bye-bye.